Hi, my name is Josh Dixon, and for my Advanced Topics in Computer Science project, I decided to investigate short text spam detection using deep learning. My project supervisors were Bushra, Sabir, and Babar. First, let's define what is spam. Many people have different definitions of what spam is, but for our project, we define spam as unwanted or unsolicited messages. This could include messages with the sole intent to advertise, messages that contain phishing or malware links, or messages that could be classified as hate speech or that contain abusive language. Next, let's define what is short text. Typical NLP techniques are applied on large samples of text, typically multiple paragraphs, meaning that they have lots of input data to work with. The classic NLP example is classifying film review sentiment as positive or negative. Then what we're working with is short text data. It's usually on the order of several words to a few sentences. Examples are SMS messages, real-time chat messages, and what we're focusing on in this project is Twitter tweets. The dataset we're using is an aggregate of two Twitter datasets. The first of which on the left is a phishing and advertising dataset. It contains 128,000 total tweets, 69,000 of which are labeled as normal or non-spam and are labeled with a 0, and then 59,000 tweets that are labeled with a 1, meaning that they are spam. Then the dataset on the right, it's much more recent. It's a hate speech dataset that came out this year. It contains 100,000 total tweets, 54,000 of which are labeled as normal, meaning they aren't spam. 14,000 tweets that are labeled as spam, similar to the first dataset, meaning that they're advertising or phishing. Then 5,000 hateful tweets and 27,000 abusive tweets. This project's really important because it aims to improve the safety of social media platform users. There are so many tweets or messages posted on social media platforms every minute that it's impossible for a team of human moderators to review every single message before it's posted to make sure that the social media platform users are safe. Therefore, an automated system is required to filter this large volume of messages. We want to decrease the rate of false positives to make the lives of human moderators easier, meaning they don't have to sift through tweets or messages that aren't spam but were classified as spam. And then we also want to decrease the rate of false negatives because we don't want tweets that are actually spam ending up on the social media platform without being reviewed. There are many challenges for this project, first being noisy input data. Because we're dealing with tweets, the language used is very informal and misspellings are common, meaning that we can't rely on dictionary lookups and stuff of that nature. The second is the presence of multilingual tweets in the dataset. Because we want to keep things consistent and simple for the models to train on, we wanted to remove all non-English tweets. The next challenge is short input text, as we discussed earlier. Because the tweets are short, typically under 140 characters, the amount of data we have is limited, so we need to use models that are able to handle the small amount of data. The biggest challenge in my mind is the use of shortened URLs and redirects in tweets. Because tweets are limited by their characters, usually URLs are shortened using URL shortening services such as Bitly. This hides the end point of the URL, meaning that the intent of the URL is hidden. Therefore, a machine learning model is impossible to determine if a shortened URL is malicious or not. Another challenge that we didn't handle in this project because of time is embedded media. So NLP techniques work on text data, whereas media such as images and video can't be easily converted into text. If we wanted to do that, we would have to use some sort of technique such as optical character recognition, which was beyond the scope of this project. To reduce noise, we pre-processed our data. We combined the two Twitter datasets, and then we combined the abusive and hateful labels because there weren't many instances of those. So we combined those to reduce the class imbalance. We filtered out non-English tweets by removing non-English characters. We simplified user mentions. On Twitter, you can mention a user by using an @ symbol followed by their username. To normalize and simplify this, we replace a username with the word user mention. We removed punctuation. We made everything lowercase. We normalized the white space, such as tabs, to just be a single space. And then we cleaned out drawn out words to reduce noise. This includes words such as like hello with 5 O's at the end. We wrote an algorithm to iteratively remove repeated characters until the word is present in an English dictionary. If it isn't present in the dictionary, the original word is used in its place. We use many approaches. The first thing we have to do is embed the text. Since text is numeric, it can't be fed into a neural network. First we have to embed it into a vector space. This can be done on either a word level or a character level. A character level is more tolerant to noise, whereas a word level model is easier to train. For embeddings, we used a one-dimensional spatial dropout layer with a dropout rate of 20% to reduce overfitting. First, we use a word level CNN. This contained 256 filters with a width of 4, followed by a fully connected network. This was trained on a dataset with both with and without stop words to compare the difference between each. We then tried a slightly more advanced word level CNN. This contained many layers of filters with different widths, with a max pooling of size 3. This was again followed by a dense network. We then tried a character level CNN. This was again trained with both datasets, the with and without stop words, to test their accuracies. This had many layers with varying size filters, followed by a fully connected dense layer. We then tried a vanilla LSTM network. This is a recurrent neural network, meaning it can handle sequence data better. It had 256 units with a 20% dropout rate. We then tried again with an LSTM, but instead of just only being able to look in the past, we made it bidirectional, meaning you can look into the future of the sequence. We then tried this again with a character level bidirectional LSTM. We then stacked the CNN and by LSTM for both the word level and the character level. Finally, we tried a BERT transformer network. This transformer network is the state of the art. It's similar to an LSTM, but it can preferentially choose the attention of which units are most important without having to feed through every other unit. We used a pre-trained BERT English network and then added 48 fine-tuned layers to train to be able to classify the tweets. These were our results. So BERT performed the best with the highest macro F1 score, and then second behind that was the character level CNN that kept the stop words in the dataset. Because BERT is such a large model and was so time consuming to train, we performed deeper analysis on the character level CNN. So here's the validations to accuracy for the character level CNN. So on the left you can see the amount of classifications that it was made for the correct label and what it actually predicted. And then on the right, for it given a correct label, what the percentage of each other category, of each other label that were actually classified as. You can see that the abuse hate speech category was best classified, whereas spam was not. And I believe this due to the shortened URLs. This can be seen in this word cloud analysis. You can see that links make up a lot of the incorrect and correct classifications of the spam and normal labels, meaning that the model wasn't able to differ between these links to be able to classify them as spam or not, whereas you can't see much overlap in the hate speech or abuse label. Future work for this project would be to explore BERT further. BERT is extremely powerful, and as we saw, it was the best accuracy. But because how long it takes to train, like it would take 8 hours for every training epoch, and it would take forever to process data, that we didn't have enough time to be able to explore this further. We would like to do extra hyperparameter tuning. We would like to explore more model architectures. To improve accuracy, we would like to do endpoint resolution if we had more time. We would like to have a better method of filtering non-English messages, and we would like to experiment with larger embedding vectors with more dimensions. Thank you.